As a wrap-up to understanding the position time graphs that are no longer a straight line but a curve, and then the velocity time graphs, we're going to look at this last page from your notes. So the first part says, write the mathematical model for the relationship between velocity and time. For that, we're going to look at the velocity time graph, and really a mathematical model is just asking for an equation. We can write specific equations for any straight line by using that y equals mx plus b format. And plugging in, instead of y and x and m and b, we use the data from our graph and the variables from our axes to kind of answer those questions. So for y, we are no longer writing y, but on our y-axis we see a variable of velocity, so a v. That's then equal to the slope. The slope is given on the graph, is 0.3, we'll round that to 5 meters per second for every second. That's our slope. Our x is no longer x, but instead we have the variable of time. And instead of b, we have the intercept, which on this one, our intercept is given as 0.1, we'll just leave it at 4 meters per second. So that tells us the relationship for this graph of velocity time, but that doesn't necessarily answer that question for all objects and their velocity time graphs. But to understand what these two numbers mean, let's take a closer look. It says write a for every statement to describe the slope. What I mean by a for every statement is talking about the slope in terms of what that number means and what those units are that apply to it. So it usually goes the vertical axis variable generally increases for our linear graphs by the slope numerical value and the vertical axis units for every, and then the horizontal axis units 1 second that passes. So this one would be the velocity increases by the amount of 0.35 meters per second for every 1 second that passes. So instead of saying 0.35 meters per second, we're really saying what this 0.35 refers to with the meters per second, and then for every 1 second that's changing. If we were to reword this, the velocity is increasing by this much for every 1 second. That is defining for us velocity changing in an amount of time. That is describing a term for us called acceleration. So notice, we just described the slope in words, kind of paraphrased it again, and then said, wow, that is our definition for acceleration. So if we even want to go full circle, back to where we got this statement from, this statement was describing the slope on a velocity time graph. So an operational definition of acceleration is the slope of a velocity time graph. So that's our new term, acceleration, changing velocity over a certain amount of time. And again, we can find it as the slope on a velocity time graph. That takes care of, for us, the 0.35 meters per second for every second, as we saw up here. But what about the 0.14 meters per second? We found that is the intercept, and the next question says, what does the intercept mean for that velocity time graph? I like to think of these as kind of some intercept statements, but at a time of 0, over 0 seconds, and then the y-axis or the y variable, the velocity is, and in our case, 0.14 meters per second. So if we were to reword this, just like we kind of did with our slope statement, this is really telling us the initial velocity. So at time equals 0, what is the velocity? Abbreviated by v sub I. Sometimes you'll see v naught. So v naught or vi is really an okay way to abbreviate that. So taking what we now know about the slope of a velocity time graph, we can kind of come down and say, well, how do we use this when we're qualitatively looking at these position time, velocity time, and acceleration time graphs? So if we remember from before, we said the slope. So the slope of a position time graph, will give you velocity. So that's kind of why I'm drawing from this position time graph, gives you the velocity. The slope from a velocity time graph, so from a VT graph, the slope gives you the acceleration. And from what we discussed before, the area under a velocity time graph gives you the displacement. So it kind of thinks it has a nice little trend there for you to think about. So when you go down from a position time to velocity time, you can measure the slope and plot a point, measure the slope and plot a point. If you're going upwards, we do know that the area under a velocity time graph means displacement. A trend actually would be the area under an acceleration time graph means change in velocity. We won't worry about that one too much. But you could also go backwards as well to plot some points or plot the graph above. So on this position time graph, like before, we picked 3 points to find the tangent. So we just kind of roughly draw them in. And then we describe the tangent qualitatively. This is a positive slope, so a positive velocity, and it's very steep, so I'm going to write my plus sign very large. This is still a positive slope, but the magnitude is just a little bit smaller, so my plus sign is going to be medium. This tangent looks just about 0. When I come down, I'm going to plot those slopes as points. So remember, this is the positive side of a velocity time graph, and this is the negative side. And then the more you are away from the time axis, or that 0 part, is going to be a greater magnitude. So if I have to plot a positive point, a large positive point at time equals 0, because we're matching our times, I can start here. The next time I'm just going to plot, so kind of down this point. The next time I'm going to plot a positive but smaller magnitude, so just about there. And the next time I have a slope of 0, so I'm going to kind of come over this way a little bit and plot it as 0. If I were to fill in my best fit line, I see that shape. It is a negative slope and just a nice straight linear line. Now, don't be confused and don't say to yourself, this has a negative velocity just because you see the slope is negative. You have to remember that slope on a velocity time graph is equal to acceleration. So if we are now plotting an acceleration time graph, you can say, well, let me take the slope at each point. Notice it's a constant slope, and at each of those points, or for the whole time, it is a negative slope. So negative, same size, negative, same size, negative, same size. On the acceleration time graph below, there's the negative portion. So you can pick whatever magnitude we're looking at as long as it's negative. And this would be the acceleration time graph for this scenario. On the next example, you can pause and try it on your own, or we can again go over how to go from a velocity time graph back to a position time graph, and then down to acceleration time. So pause it and try it on your own if you want to, and if not, we'll keep on going on. Okay, when you have 2 graphs to fill in, and the middle one is the one that's given, I tend to like to drop down to the graph below first, because that one just is a little bit easier to do. So I have a velocity time graph on my axes. I could describe this as negative velocities. So the object is moving in the negative direction the whole time. Just a side note on how to keep in reference. I start off with a velocity of 0, and then my speed gets greater. So therefore I'm speeding up in the negative direction. That is kind of how to read that graph. But if I'm plotting an acceleration time graph, I have to take my slope at certain points, and I have a negative, 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 same size slope. So that tells me my acceleration is negative. I come down to my acceleration time graph, plot those accelerations, and I see a horizontal line. Notice these two graphs, which are different situations. One is slowing down as it moves in the positive direction, and one is speeding up as it moves in the negative direction, have the exact same acceleration time graph. So again, that's practice going to the acceleration time graph from the velocity time graph, but let's go back up to that position time. This is the one where I like to read points off of our velocity time and draw in tangents above. So I read off this point and my velocity is 0. So that means I'll need to draw a slope of 0 above. At this point, my velocity, I kind of bring it across to your y-axis. You see that this velocity is negative and it's a medium negative. So I'll leave that there. As you come to the last point, you read across to the y-axis, and this is a very negative velocity, or a very large negative velocity. So with that being said, we need to draw 3 little slopes up here, and 0 slope to negative medium slope, and then a big or steep negative slope. To think about that, I'm just going to draw a little key up here. You can think of a positive slope, or 0 slope is going to look like this. A positive small slope, a positive medium, and a positive large slope is going to look like this, this, and this respectively. So negative slopes, a small negative, large, medium negative, and large negative slope are going to look like this, this, and this. So that's kind of my key for reading these velocities qualitatively and drawing those slopes or tangents on that position time graph. So at time equals 0, I need to start off with 0 slope, and because I have done a lot of these, I know I should probably start it above here. If you started it somewhere else, that's okay. At this time, I need to draw a medium negative slope, and at this spot, this time above, I need to draw a steep negative slope. If I connect those, I get this nice curve. So the position time graph would look like that for something that has a velocity time graph looking like this. That's the general idea of switching back between drawing these graphs from xt, vt, and at.